So we're going to begin a series of topics that, for lack of a better term, we'll group under the category math. And this might seem like a sort of weird topic to think of as a sort of sub area because pretty much everything we do has math in it, and we've been using math all along in this course and so on. But in particular, I want to talk about a few things in this section. In this particular recording, I'm going to talk about different patterns of numbers, number sequences, permutations, combinations. Later on, we'll talk about primes and about modulus and about some things like cycle finding. So math, the reason that we want to sort of study this as an area for problem solving is that many times math can be used to simplify a problem that is much more difficult looking than it actually is. Something where if you analyze it mathematically, you can simplify a lot of the work that's there into something that's much, much simpler. And that's kind of the key part of all of this is it might be very difficult to compute something if you don't understand the mathematical relationship between the numbers. And if you do understand them, all of a sudden everything becomes a whole lot easier. So we've seen this a lot already when we talk about brute force. So when we discussed brute force methods, we would look at ways of, say, limiting the range over which we were examining values, and you might have to analyze a problem mathematically to find the range that something went in. We might find that you could compute one number based on the results of another number. So for instance, if you had to find something like n1 squared plus n2 squared, you might you're wanting to find where it equals some value d. Well, if you just iterate through n1, then you can just compute compute d minus n1 squared and take the square root of that, and this is going to be what n2 is. And so by mathematically saying we know what the equation for n2 is, we don't have to iterate through the values. We don't have to check all of them. So we could maybe only iterate through one of them. Okay, so that's the sort of reason why we would want to use these mathematical forms. And a lot of this sometimes in terms of figuring out how something will simplify is really just pattern recognition. It's a matter of looking at a problem, and everyone does this. In fact, this is one of the ways we learn the best is we look at things, we see lots of examples, and we deduce the pattern. And that's deductive reasoning. And deductive reasoning is the way we learn a whole lot of what we learn. It's one of the main ways we learn. You often get taught inductively, where you learn a principle and then are supposed to apply it. But the way you actually learn is usually deductively, where you see examples and you recognize them. So most people are pretty good at pattern recognition, better than you might think. And so the idea here is you basically try a few values, and then you see if you can recognize a pattern. Now, if you're actually applying this in a situation where you really need to know the answer and rely on it, you eventually will want to then prove whatever you find. But in most of the types of things that we're dealing with in this class, we're not going through the proof process. We're just looking to see, can we recognize it, and realize that, yeah, you might recognize the pattern and you might be wrong. You might recognize the wrong pattern, or you didn't look at enough terms, or you didn't think about something else. So in a real world situation, you do need to then go through, after you've found a pattern, and prove that that's the correct thing, that is in fact the pattern that you're seeing. But at least in terms of problem solving, it's often enough to be able to generate a few examples by hand or even on the computer and see, hey, do I see what is happening here? Is there a way to recognize what's going there? And in particular, one of the things in patterns is to look for well-known sequences. So I'm going to spend some time talking about some of the well-known sequences and some of the, in addition to well-known sequences, some of the what you might call special numbers. And this is things like combinations and permutations and so on. And so we'll talk about a few of these different terms here that we have. So one of the most important ones that we have are arithmetic sequences. And these are ones where the difference between one value and the next is a constant factor. So if I subtract one number from the next one, I always get the same value. And so what we have is we have numbers that are set up where a sub I is going to equal some base. And maybe I shouldn't have used a here, but normally the base is a, and there's some factor b, and you multiply it times I. So a plus b times I. So a sub 0, you would probably say is a, and a sub 1 would be a plus b. And a sub 2 is a plus 2b, and so on. Okay, and so if we were to take the sum of a0 to a n minus 1, so these are the first n terms, this would be the value n times a1 plus an over 2. Okay, and the way that you often will see this is where a is going to be the sorry, not a1 to an, it's a0 to an minus 1. N times a0 plus an minus 1 over 2. And an example of this that you often see is when basically when a is nothing, then, and you end up starting with a1 effectively, or you can also think of it as the value of a is equal to b. This is where you get the very common n times n plus 1 over 2 to get the sum of the numbers from 1 all the way to n. Okay, so the sum of the numbers from 1 to n is n times n plus 1 over 2, but this is the more general term here that you can use. So the other type of sequence that you have besides an arithmetic sequence is the geometric sequence. And this is where you have a ratio of one number to the next. So you have a times r to the I. And so a sub I equals this. So a0 would be a times r to the 0, or the 0 is 1, so this is just a. a1 is going to be a times r. a2 is a times r squared. a3 is a times r cubed, and so on. So an arithmetic sequence, this often comes up when you're applying some factor to something. You multiply it and so on. One of the most common sequences that we have is a declining geometric sequence where all the values are going down. And that's where r is less than 1. So everything keeps shrinking and shrinking and shrinking. And in that case, we actually have a nice formula. We can say the sum of a0 to a n minus 1. Again, this is the first n values, is 1 minus r to the n over 1 minus r times a. Okay, and so this formula, it only works as far as less than 1, but it's a simple way of summing up a bunch of values and seeing what they are. So for geometric sequences, for arithmetic sequences, we've got those nice properties that we can use along the way. Now, that's part of pattern recognition. I'm going to get to a few other types of numbers and patterns of numbers in just a little bit. But let me talk about a couple of other things that you can do. So one of the things that you have available, kind of a trick that you have available, are logarithms. And I want to remind you of the power of logarithms in terms of simplifying computations, is that they will convert multiplication to an addition, and they convert a power to multiplication. Okay, so remember that if I have the log of a times b, this is the log of a plus the log of b. And so sometimes it's easier to do addition than it is to do multiplication. And so you can use the logarithm to simplify that. And likewise, if you have the log of a to the b, this is b times the log of a. Okay, so again, rather than taking a power of something, you can just multiply. And in particular, this is one of the very powerful ways that logarithms get used, so that you don't have to take large powers. You can just do a multiplication in the log, and then again, you raise something to the power, whatever the base is. Or you raise the result to whatever the base is, and you've computed what your power would be. And so even though most people, if you're taking a power, you're using a built-in function that's provided in the language, there are times when you actually want to perform some of these things yourself, and logarithms are your friend for doing that. Another thing just to keep in mind is that if you ever have the log of a and it's in base b, this is equal to the log of a over log of b in any other base. Okay, so you can always convert between different logarithmic bases just by doing division of the logarithms. So keep that in mind. You can use logarithms and the I mentioned a little bit about using them for powers. One of the reasons that you might want to replace multiplication with addition is you might have an algorithm that works for computing something under addition, but it doesn't work for computing it under multiplication necessarily. That's not the way it's set up. And if you just convert your problem to one that is based on addition, then you can use your standard algorithm and then at the very end convert it back to the other value that you had. Now, I should mention one other thing related to all of this math stuff, which is number storage. And this really does become an issue when you are doing a lot of these mathematical computations. So for one, we've talked over and over and over in here about the precision that you need for integers and the need to use long integers in many cases. But in particular, when you're doing some of these mathematical computations, you could end up needing long integers. So and by this, I mean arbitrary length. And this is where you actually have it's one of the few cases, I would say, where you have a clear advantage of Python or Java over C++. So for Python, this is automatically built in. So integers are arbitrary precision. You just keep adding digits on as many as you need. With Java, you have a big integer class. And in C++, there are actually many libraries out there that provide support for big integers. The Boost library, for instance, has some of that, but it is not a built-in feature of the language itself, so it's not part of the standard library. Now, if you are using these arbitrary length integers, that means that you're not going to overflow, you're not going to have something that's too long, but the downside is, so the positive is you don't run out of digits of precision. And the negative side of all of these is that the math is slower. Okay, so it is slower to add two arbitrary precision integers than it is to add something that's using the native integer type that is supported in hardware. And the overhead to handle, there's a lot of optimizations you can make if you ever look into this, where it's not really bad. It's not a whole lot worse if your numbers are small. You just sort of say, hey, this is a number that fits into a standard integer. I'm going to use all the fast stuff. But there's still that little overhead of checking, hey, is this a fast integer? Can I use the standard hardware, or do I need to go to a different algorithm to compute my values? And so the thing is, no matter what, the math is going to be a little bit slower, and sometimes it can be a lot slower. Now, in Java, the big integer class, it also supports a lot of other operations, and so including some of the things we'll talk about in future math lectures about computing GCD and doing modular arithmetic and probabilistic primes and all sorts of things like that. Okay, so just realize that you need that. The other thing is related to number storage is your floating point values. There are many things where the operation that you get gives you a floating point number back, for example, square root. And the thing to remember is that you almost always have round off. And pretty much you should just, anytime you have a floating point number, a double, a float, whatever, you should just always assume I've got round off error in there. And if you're trying to do precise comparisons between numbers, you have to be really, 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 really careful because and typically you need to actually keep some sort of bound and check within epsilon. See, you say, if you want to say is A equal to B, well, then what you would do is you would take the absolute value of A minus B and see if that's less than or equal to some little value epsilon. So you might set like 0.00001. Okay, and if that's true, then A is equal to B. Okay, so rather than checking are those two things equal, you instead perform that comparison. And that's obviously a lot of overhead. It's a lot of pain to do that. This is a topic near and dear to my heart because it's very closely related to what I did my dissertation work on. But the main point here is if you're ever using floating point, you need to be really careful that you are not, you're not going to be assuming that things are not rounded off when they are. Okay. So let's go to a couple of the types of calculations that we need to do. One of these is going to be permutations. So we come up with permutations all the time. We run into them over and over. You may remember that we talked about generating permutations earlier. So this is generating every possible permutation of something. But in terms of counting permutations, there are times that we want to count them. And so And so the number of permutations that you have for n objects is going to be n factorial permutations. And just in case you happen to forget what n factorial is, this is going to be n times n minus 1 times n minus 2 all the way down to 1. That's what n factorial is equal to. Okay, and you can compute n factorial if you sort of work your way up. You know, you set it equal to 1, and then you multiply that times 2, so you get 2, and you multiply that times 3. So you go from 1 to 2, multiply that times 3, you get 6, multiply that times 4, you get 24, and so on. And this quickly becomes a very, very large number. So in particular, a long int will hold only up to about 20 factorial. So you can't get bigger than that with a standard long int. And so anytime that you're doing calculations that have factorials, you need to be careful and say, is there some way I can simplify the computation? Can I reduce it where I don't have to compute the entire factorial? When we talk about combinations in just a second, this is part of what comes up. The other thing that we will often run into is if you're asked to count permutations, you'll be asked to count them modulo some number. Okay, we're going to talk about modular arithmetic in the future, but the other way that this would come up, and it might say, well, you know, count the number of permutations up to 100, you know, of 100 items. And you can do that modulo some value. Well, modular values, the idea is it's always going to fit within typically a standard integer. And so you can perform your multiplication in a long integer, and then you take the modular arithmetic and it's back down to an integer size. So just keep in mind that modular makes larger values possible. And again, the types of problems where you come up are you want to figure out how many different ways are there to do X. And so calculating that, those number of permutations is the typical type of problem you would see there. Now, one thing I should mention, I said n objects, you get n factorial. If some objects are repeated, and so this would be n1 times, and 2 times, etc. Then the number of permutations is going to be n factorial over n1 factorial and 2 factorial, however many nk factorial, however many k's there are. So, if you say I've got 3 of type A and 4 of type B and 5 of type C, so there's a total of 12 items, this would be 12 factorial over 3 factorial, 4 factorial, 5 factorial. This would be how many different permutations of those letters A, B, and C are. Okay, if 3 A's, 4 B's, and 5 C's, there would be this many permutations of the whole thing. All right, the other value that we need to consider are combinations. And combinations are probably the most commonly used thing that we run into. So the basic idea of a combination is we say how many different ways can we select some number out of some larger number. So normally we would write this as C of nk. So this is choose k from among n items. So if there's n items, you want to choose k of them. You'll sometimes hear this written as n choose k. You'll sometimes see this written as nk. That's the common way that that's written. The other way that you will sometimes see this written is c n k. All of those mean the same thing. It's the way of choosing k from among n different items. Now, the way that this is defined, and it's probably the way you learned it, is that this is going to be n factorial over k factorial and minus k factorial. Okay, this is going to be, that is equal to n choose k. And the only problem with this is that if you use this formulation, it sometimes is difficult to calculate. In particular, if n is a large value, you don't want to actually compute that numerator, and it will often cancel out. So, let's just say we had something like 12, choose 1. How many different ways are there to choose one item from among 12? Well, the answer obviously is 12. That should be obvious. But if I went through and calculated this formula, I would first of all have to calculate 12 factorial. That's a big number. And then I would have to divide by 1 factorial and by 11 factorial. And if you just look at how these cancel, 12 factorial is 12 times 11 times 10 times blah, 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 all the way down to 1. 1 factorial is just 1, and 11 factorial is 11 times 10 times all the way down to 1. Well, all of these things are going to cancel, and so you're left with 12 over 1. So it's kind of, which is equal to 12. So the answer that you end up with is much smaller and a whole lot less work than it might be to compute the whole thing. Now, there are a couple of ways of computing these, and the most commonly known one, and one of the most efficient ones for computing things if you need a lot of combinations, if you're trying to compute pretty much all of the combinations up to a value, is you use a dynamic programming approach that is called Pascal's triangle. So I'll mention to you kind of the DP formulation of it, which is that C of nk is going to equal C of n minus 1 k minus 1 plus C of n minus 1 k. Okay, so this is going to be the sort of recursive definition of how we can compute a particular combination. And that prevents us having to compute all these factorials and cancel them out and so on. Now, the way that you've often seen these, and you'll often see this written, is with Pascal's triangle. And Pascal's triangle is a way, it was sort of the way it's normally thought of, is it's the coefficients of, if I were to take something like x plus y to the n, what are the different coefficients? So, you would end up with something like x plus y if n is 1. If n is 2, you would end up with x squared plus 2xy plus y squared. So the coefficients here are 1, 1. The coefficients here are 1, 2, 1. If I were to take the cube, I would end up with x cubed plus 3x squared y plus 3xy squared plus y cubed. So the coefficients are 1, 3, 3, 1. If I'd actually done it to 0, I would have just ended up with the number 1. So it was like that. And so this here is Pascal's triangle. And the way, and so these coefficients that you have of the individual terms, excuse me, the kth coefficient of x plus y to the n is c of nk. Okay, so those combinations are the coefficients of this value. Those are what the combinations are. And so Pascal's triangle, if you want to compute this, this is a simple way of computing your c values all the way up to wherever you need them. And the way you would do that is you start out with 1 and 1 and 1, and then at each value you can think of putting a 1 on the beginning, and you're always adding the two numbers up above, and you go out one more. So 1 and whatever was before it, that's nothing. Add those two together, that's 1. You add these two together, you get 2, and then you add these two together and you get 1. So now I'm going to add that. I get 1. I have 3, I have 3, and I have 1. I do this again. I get 1, 4, 6, 4, 1. Okay, and each one, you're just adding up the things for the next level. So this would be 1, 5, 10, 10, 5, 1, 1, 6, 15, 20, 15, 6, 1, and so on. And it's very easy to generate all of those combinations, all of those combinatorial values by doing this way. So let me give you just a couple of quick examples of ways that you can use combinations and combinatorics. So let's say that you want to choose k objects out of n. And this is more of a definition. It's one of the things. You can prove why this is the case, but you want to choose k objects from n, but allow the same thing to be chosen repeatedly. So if we were just choosing n objects from k, that would be c of nk, but this is going to be c of n plus k plus 1 k. Okay, that's what that value is. Another one is, and it's actually kind of the same thing. This is equivalent, and you'll have to convince yourself of why this is the case. If you were to say divide k objects into n containers, it's also that same value. Okay, so both of those come up if you're dividing objects into containers, or you're selecting objects, allowing them to be chosen repeatedly, you get the same value there. Okay, but let's give an example. Let's say that we're given a grid. We're given a bunch of lines here and a bunch of lines here. And I want to say, how many possible rectangles can I form in that grid? So I've got, well, there's a rectangle. And, here's a rectangle, and here's a rectangle, and there's a rectangle here. And, I could just come up with lots of them. And so the way to think about this, like if you said, how would I enumerate that? Well, generating every rectangle would be a problem. You couldn't do that. But if you just wanted to count how many there are, if you wanted to count the number that you have, you could say, well, what I want to do is I want to pick 2 vertical lines out of, in this case, 1, 2, 3, 4, 5, 6, 7. So I'm going to have from 7, I'm going to choose 2 vertical lines. And then I'm also going to have 2 horizontal lines. So out of 4, I'm going to choose 2. So 7 choose 2 times 4 choose 2. And if I wanted to, I could figure this up. I don't know what it is off by hand, but that would be how many rectangles you could find out of that entire grid. So it's actually just a relatively simple mathematical computation, whereas the process of actually generating them would be just totally infeasible. Another example is if you wanted to calculate like the number of different ways to get from one point to another, you'll often say, well, I can pick from n different paths, and I've got 7 paths. I can pick any 2 and get to different places and so on. All right. So the next topic that we want to talk about is going to be some special number sequences. And I'm not going to go through these very much, but I'll just mention them briefly, and you can look at them if you are curious about them. But they are numbers that do come up occasionally. So the Fibonacci numbers, if you remember, Fibonacci numbers are where you have 0, 1, and then every number after this is the sum of the 2 previous numbers. So you would get 1, 2, 3, 5, 8, 13, and so on. And Fibonacci numbers, we've talked about these with dynamic programming. We see that that's how we can compute them and so on. They can get large, just like anything else. There's some interesting properties. These will pop up in lots of different places you might not expect them. So it's a pattern that you ought to be attuned to, so that if you see that pattern pop up, this kind of 1, 2, 3, 5, 8, 13, then think, oh, if I'm adding those 2 previous things, I'm getting something like a Fibonacci sequence there. And you might or might not be able to use the fact that it's Fibonacci, but at least you can know, oh, I've got this kind of dynamic programming approach that I can use to generate the numbers if I need to. Now, there are some interesting properties of Fibonacci numbers. There's a theorem called, and I love this name, Zeckendorf's theorem. And Zeckendorf's theorem says that every positive integer you can write as a sum of Fibonacci numbers, and no 2 Fibonacci numbers are consecutive. Okay, that's really weird. It's very non-intuitive to me, but it basically says if I have any number that I want, I can write it as a sequence of Fibonacci numbers that are not consecutive to each other. So let's say that I pick the number, 21. Well, obviously it's 8 and 13, but those are consecutive to each other. But I could write this as 13 plus 5 plus 2 plus 1. That would be 21. And so it would be 13, 5, 2, and 1 would be the number 21, as an example. So that's an interesting property. Again, it's difficult to see how you would use it, but I guess it could come up. There's also something that's interesting called the Pisano period, which basically says how frequently the digits of a Fibonacci sequence repeat. So the last digit will repeat every 60 numbers. The last 2 digits will repeat every 300 numbers. The last 3 digits will repeat every 1,500 numbers. And the last 4 digits will repeat every 15,000 numbers. Okay, so anyway, just weird things having to do with Fibonacci numbers. They're a lot of fun to look at. It's mainly just a sequence that it's useful to recognize. Finally, the other one to mention are Catalan numbers. And the way that these are defined recursively is that cat of n is going to be sorry, that is going to, I'll write the base definition. It's C of 2 n, choose n over n plus 1. The and cat of 0 is equal to 1. And so the recursive definition is that cat of n plus 1 is equal to cat of n times 2n plus 2 times 2n plus 1 over n plus 2 times n plus 1. And I believe I've done that right. So, so you can generate these recursively, kind of a dynamic programming approach. But Catalan numbers, actually, they pop up more than you would realize. So some examples, if you want the number of distinct binary trees with n vertices, so I say I'm going to have a binary tree and I've got n vertices, so say the number is 4. So there's a binary tree with 4 vertices. This is also a binary tree with 4 vertices. This is a binary tree with 4 vertices. How many are there? Well, the Catalan number tells you, the cat of n tells you how many possible binary trees there are. If you want the number of different ways of parenthesizing something, so like if I've got n plus 1 factors, so I've got a, b, c, d, e, okay, so in this case there's 5 factors, so 4. Cat 4 would be how many different ways can I parenthesize these to compute this whole value? Okay, so that's one possible way of making parentheses. A different way of doing the parentheses there would be maybe I do this, and then I do that, and then I do that. Okay, so that's a different one. So cat 4 would be that. There are ways of saying if I have, and we'll get to geometry later, but if I have a convex polygon and I want to triangulate it, there's different ways I could write the triangulation. So I might triangulate them. So there's 2 of them. How many different ways of doing that? You can use Catalan numbers to do that. If it's got n sides, it would be cat of n minus 2 would be the number of ways to triangulate a polygon. Okay, so this comes up a lot in various ways that you might not expect it to. Again, Catalan numbers are also interesting to look at if you're just curious about kind of cool number sequences that have some different uses. Okay, so that's our introduction to a bunch of mathematical things, kind of a wide variety of stuff. Probably the most useful of all of them are the combinations and computing combinations, but recognizing patterns, different sequences, permutations, combinations, and some of these special number sequences are all things